Well, good morning and welcome to our Cosmic Conversations here on the Morrison Planetarium Facebook page and OpenSpace YouTube page. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences in San Francisco, and I'm joined by Alex Bock, who's the lead developer for OpenSpace based at Lynn Shipping University.
Good day.
Well, it's always fun to use these times on Friday to kind of geek out on astronomy topics. This one is particularly kind of fun for me, I think, because we're going to geek out on how visualization tools can bring 21st century astronomy into planetariums and now desktops and elsewhere. I've been working in planetariums as of next year. It's frightening to think, but about 30 years. And I've always had the opportunity to work in digital planetariums that have data as a basis for what we're showing audiences. But now the tools have become much more accessible, and I think that's why it's really great to have Alex here to talk about kind of the future of not just digital planetariums, but digital technologies to bring the universe to people around the world. And so we're going to be talking about OpenSpace, an open source astronomy visualization tool that Alex probably knows more about than just about anybody. So I think we're going to start out at Earth, and I think part of what we wanted to touch on were the challenges of the various kinds of data that all kind of get funneled into software such as OpenSpace. And so maybe, Alex, you could just start us off talking about some of the challenges and interesting aspects of bringing all these data layers to life.
Sure, absolutely. First of all, it's great to be here. I've been following the shows for a while now, and it's nice to participate in them now as well. So as you said, we're starting at Earth, and one of the first things that might not be super obvious when we're looking at this is that already now we're looking at quite a large amount of data just by looking at the Earth from this far away. So we're seeing the clouds is taken by the SOMI NPP satellite, and those are spanning around the Earth. They're updating every day. So for instance, now since it's all interactive, we can go back an entire day, and now we can see in real time as my computer here is now fetching the data all over from here in Sweden, going to the west coast of the US where the data is stored, and then coming back again here. And we can actually see that the transition of the internet packages happening live. And so one of the really nice things that has really made this possible in the last couple of years is the immense amount of power that our computers nowadays have. Even if you just go to Best Buy and get the cheapest laptop you can get, if you would time travel back to 20 years ago, you would probably be in the vicinity of the most powerful computer that you could possibly have at that point. And even just looking at things like an iPhone, for instance, those would be considered supercomputers just mere 20, 25 years ago. So this immense explosion of hardware has really made it possible for us to do all of this. So just downloading all of the data on the fly, and of course the internet speeds and so forth. And particularly now with the internet, that makes it much more easy to share all of this as well.
Yeah, the American Museum of Natural History is one of the collaborators in New York, is one of the collaborators on this software project, and actually they started a similar kind of digital galaxy, digital universe project about 20 years ago, and it really was running on a supercomputer just to drive what is probably fewer pixels than we're pushing through the web right now onto the planetarium dome. So
exactly. So the stars actually in the background, they are coming from that digital universe catalog. So we have the accurate 3D positions of all of the stars, of quasars, of galaxies, and some of the data sets that we have here, they're definitely scratching on the terabyte data sizes, which would be just impossible to even store, let alone handle on a separate computer. So that's really nice. But yeah, for instance, what we can do is flying into California, and let's see what happens as we're flying in. Because right now we're seeing, as I said, the cloud layer, but as we're coming in, we're transitioning over to a much higher resolution imagery. So the cloud layer, as I said, comes from a NASA satellite. It's about 0.5 kilometer resolution, which means that every pixel covers about 0.5 kilometer on the surface of Earth. But now we're flying into a data set that is curated by helpers from the people that we collaborate with from Esri, and this one is much higher resolution, so we can fly in closer and closer.
Well, there's kind of this trade-off too of like temporal resolution versus spatial resolution. So for the cloud data set, it might be kind of low pixel resolution, but we're getting it every day. So whereas this image of San Francisco that we're flying into isn't something that's updated every day, but has much higher resolution as we approach our beloved California Academy of Sciences here in Golden Gate Park.
And probably for privacy reasons, also a good idea that this high resolution doesn't get updated every day. But like if we, for example, look at this right now, we have a nice view over Cal Academy with the Golden Gate Bridge in the background, and you would think like you can already kind of see that the resolution as we're looking at up here closer is higher than what we're doing back here. This is one of the trade-offs that we have to do in a lot of places where we can't render everything at maximum resolution, even with the powerful computers that we have. So we need to do trade-offs. And one of those trade-offs is the further something is away, the less we're interested in its detail. So one of those things that we can see in this, what we call our globe browsing layer, is that we have this ability to load individual chunks of the planet Earth in individual chunks, essentially. So what I can do here, if I bring up the menu, we can actually look at how these chunks look like. So if I turn this on, this is one of our debug options. So it's not normally something that we would want to show, but people can explore, right? It's and here the thing to keep in mind is that every square that we now see has the same pixel resolution. So every square is covered by, in this case, 512 by 512 pixels. And you can see like the closer we are, the smaller those squares are on the surface, which gives us a higher resolution. Whereas as we look over here, like the entire Bay Area over here is just covered by a single square because we don't actually see that much detail in there anyway.
So you put the pixels where you need them.
Exactly. And also save the computer's processing power.
Right.
Because if we have, I don't know, 20 pixels that end up in the single pixel on the screen, maybe that's a bit too much.
Right.
But then we can interactively change the resolution, and you can see how both the image resolution changes as well as the tiling on the surface. And this goes all the way out. So if I start lifting again, so you can see the further something is into the distance, the lower resolution it is, until we're getting all the way to the full planet, which we represent by 8 of those images. And for instance, what we could see, maybe people recognize or realize that when we're going back in time, when the images were coming in, naturally, all of those images, they come in exactly on those boundaries. Mm-hmm. So like every time there's some images that are missing, I mean, of course, those are the images that are missing. So we're showing the ones that are in these tiles. So that was one of those really nice things with OpenSpace, that it's both an academic as well as a public presentation tool. And so this was one of the papers that we wrote at the Visualization Conference, which in 2018 got the Best Scientific Visualization Paper Award as well for exactly this system.
A lot of this work is actually being done by students as well, right?
Exactly. So this globe browsing system was started by Kalle Bladin and Erik Broberg, who were master students here at Linköping University. And it was actually their master thesis work to implement the system and come up with some optimizations on how to handle multiple layers and all of that stuff. And then they wrote the paper about that as well with the rest of us as academic supervisors. And yeah, we've had about 25 master theses so far over the last couple of years. Some of them have made it into the release, which people can freely download and look at. Others are not yet ready, so there's always this trade-off as well, of course.
So really, when we talk about this software, we're talking about the opportunity to show really awesome astronomical data to large groups of people. but there's a kind of research component that crosses not only research for astronomers, which I hope we'll probably get to a little bit later, but also the kind of the sort of, it's fair to call it engineering research into how to create high performance software.
Exactly. So, I mean, I did my PhD in visualization. So I'm like, one of my hats is definitely very firmly rooted in that, to come up with new visualization methods that are useful for domain scientists that maybe they haven't thought about before. And like, one of the big interests for me personally is the communication of science to both of science and the act of science to the general public. And this is where the contextualization, for example, on planetary surfaces comes in. Like, if we just show people an image of, let's say, curiosity, like it doesn't really give that much meaning. But if you're flying around the orbit and then fly in directly to that location, you actually get a sense for the vastness of the scale of everything. And that's like one of those things that really helps.
Well, and also I think what's really important is context, because, if you're looking at just one small feature, then being able to understand where it resides in this larger environment is really important. Like knowing that San Francisco is on the U.S. left coast.
Exactly.
Well, actually, since you mentioned Curiosity and Mars, maybe that's a good excuse to show how some of these same tools work on Mars in terms of in terms of really being able to bring to life and provide context for the just phenomenal amount of data that's come back to us from multiple spacecraft missions to Mars.
Yeah. So as I said, like, everything we want to provide in its proper context. So here I'll just fly out, and we see the orbit of the Earth as the blue line. And zooming out a bit more, we can get a good look of our entire solar system. Now, if we set our focus to Mars, so within the same scene and everything, we'll just seamlessly transition over to the red planet and its two moons. So this is one of the other academic parts that we just finished, actually. So 2 weeks ago, there was the big visualization conference where we presented one of the newer papers that we did on the atmospheric model inside of OpenSpace. That's one of those things that we haven't integrated into the public version yet, because it's not running as fast as we wanted to. But it's at the moment one of the state-of-the-art implementations for realistic atmospheric renderings, which I'm very proud of.
So if you introduce it to the public version, you'd be dragging everybody's gaming machines running OpenSpace down into a few frames per second as they try to render it.
Exactly, and it works really well when you're looking at every individual things by themselves. But if you at the same time, but I don't know what people want to use OpenSpace for, and that's a good thing. So we have to provide the ability to cobble together everything. So, and it still needs to run. So that's one of the big interesting things, but also challenging things.
Very cool.
So we are here at Mars, and one of the nice features, of course, Olympus Mons we have up here, which, if we're looking at it on the limb, we can actually see how it sticks out of the atmosphere. So that's why it's its slightly darker color. We have the Valles Marineris. It's deeper, so it's lighter here because it collects more of that dusty atmosphere in Mars.
Wow.
So one of the nice data sets that we have here, which we can enable, is called the CTX data, which is the context camera taken by the Mars Reconnaissance Orbiter. So it's a orbiter that I think last year finished its 50,000th orbit around the planet, and has been taking constant pictures of the surface. And here the nice thing is, I can explain this now, that it's taking polar orbits and it's flying over the same place and blah, blah, blah. And it's like, it doesn't really explain it in the same way as if we now just turn on the layers and we can see actually the images that it have taken. And now you can actually see the trajectory of the spacecraft immediately, because you see all of these strips that it has been taking, because it's flying over a location, turning on the camera for a bit, taking that image, turning it off again, and that's where we end up with all of these strips. So this is a beautiful representation or visualization of the path of the orbit, which is, I think, very fantastic.
Yeah, it's very cool.
And here, same thing again. We can fly in. And now the CTX camera has a resolution of about 6 meters. So every pixel covers 6 meters of resolution.
So basically, when we looked at the Earth data, someone or many people took the time to do all kinds of smoothing and making sure that all of the colors matched. The trees in Golden Gate Park look the same color as trees in other parts of Golden Gate Park. But here we're actually seeing kind of more like raw data, where where we're seeing the limits of those, like you said, the CTX individual images mapped onto Mars's surface. So it doesn't quite have the polish, but like you said, it really underscores the data part of the story.
Exactly. We do have a blended version of that, which tries to blend those things together, which, like, depending on the story that you want to tell, one is better than the other. This one's coming from some server in the US, which takes quite a long time for me over here in Europe. But the nice thing is, like, from the software point of view, it doesn't really matter if you're looking at Earth or if you're looking at Mars. So here we have exactly the same thing. It's like we have the tiles, the closer you are, the higher resolution. And now with these dramatic formations on Mars, we also have the height information, which also gives an important context for the data. So for instance, if I just disable the height information, it's still the same pixel information that we're getting, but you're getting a much worse experience of the actual dramatic structures of the Martian surface.
And the height data has the same kind of stitching issue that the imagery has, correct? So sometimes you have good height data for one part, but not so good for another. So how do you deal with that?
So we're actually not dealing with that at all, because we don't want to, on purpose, we don't want to portray information that we don't actually have in the data. So one relatively easy way would be to somehow smoothly transition between those areas, but that creates height information that is not actually there. And maybe there's even a good story to be told about that. So for instance, we're right here, we have Western Condor Chasma just across. So what I can do is, if I turn on one of the higher resolution levels over here, we can actually see that happening. So that one is called Southwest Condor Chasma, and we have it right here.
Cool.
So one of or the creative lead of the project, Carter Emmert, he calls it the bathtub, because now you can here at the borders, you can actually see where those height layers don't match up, because the image layer that I just enabled, or the height information for it, has a higher resolution. So of course, it would be very weird if they did match up, but we're actually not. We are highlighting that difference.
So we had a request to ask if we could go to ground level on Mars, and I guess with these data on, this might be one of the best places to do it.
Yes. So we're basically close to ground level as we can get right now. So these hills, they are about 40 to 50 meters high, maybe. I don't know what that is in feet, but this is basically human scale. So the image data that we're looking at right now comes from an instrument called HiRISE, also on the same orbiter, which has a resolution of approximately 25 centimeters. So basically a football per pixel. So if there would be anything in human scale here, we would definitely be seeing that now.
European football, though, right? Oh,
yeah. Or isn't it the same size?
But actually, what's kind of cool here is that with this, and I guess what's important to note is this is all data that's been acquired from orbit. This isn't like a lander like Curiosity. This is all being seen from space and then reconstructed in 3D and placed into this environment.
Exactly. So it's basically the Mars Reconnaissance Orbiter was taking two pictures of the same location from slightly different angles. And the same way as we are seeing stereo with our two eyes, because they're slightly offset, you can use the same idea to reconstruct this height information.
Very cool.
Particularly here on Mars, even though it's still the old atmospheric model, it looks fantastic to look at a sunset. Since it's so much CO2 in the atmosphere, you actually get blue sunsets rather than the ones that we're familiar with.
Yeah, Mars is sort of the opposite of Earth. We have the blue sky and red sunsets, and on Mars you get kind of the reverse.
Exactly. But here's also one of the things that I want that we could talk about is space is really big. That's not really a big surprise, but our computers, they have usually a fairly limited range of numbers that they can actually represent. So what we normally do in computers is what's called floating point numbers. So you can imagine as just something, comma, something else, and then we can move that comma around. That's what the comma can be floating. That's why it's floating point. But that gives us only limited resolution. And usually the amount of numbers that we can represent is about 10 millionth of a number. So if I'm looking at the number 1, I can represent up to a millionth or minus a millionth, but nothing in between. Like if I'm doing something in the middle, it just gets truncated. So that's kind of potentially a problem if we want to look at things. So for instance, now we're out here on Mars. So we're 2.5 AU away from the sun. So if we're at this point with a camera, we are actually, we would be seeing some of the issues that this floating point the limit of the resolution would actually give us. So this was one of the work that one of the contributions from Eric and Kalle to actually implement what we call a camera space rendering. Because for instance, if I were to take off their implementation, which I can do up here, the other way around, and maybe I'll need to turn on the layers again. So I'm not sure how much of that is going to be visible on the stream, but it's now nice and not really smooth anymore. And you can also see the lines up here, they're not really that smooth anymore. And this is actually now we're seeing the limited resolution of the computer at its best. So, or worst, if you want to say it that way. But if we switch over to the other method again, it becomes buttery smooth.
Very nice. So this is basically that jitter is because the computer is it knows where it is, but there's a little bit of uncertainty in a sense of exactly where it is. So from frame to frame, it's like, oh, I'm here. Oh, no, I'm over here. And so you get
it's just jumping from, it has basically 2 numbers that it can represent, but the true position is somewhere in the middle. So it just bounces back and forth between those 2.
Very cool.
So, but one of the the drawbacks with this method is that we're actually, so if we're rendering everything smooth and nice, we're actually assuming that the planet is completely flat, which naturally is not the case. So that's another one of those trade-offs that we have to make. So for instance, if we were to fly up to the orbit level again, I'm not recommending anyone doing this. This is for illustrative purposes only. But if we dial this up, that we use this flat planet rendering method, way too far. So you can actually now see over here how the planet is represented by multiple flat spheres, which we have to do at lower levels. But of course, in orbit level, it doesn't really make any sense at all. So we'll just take that away quickly.
So then part of the challenge is sort of choosing the tool that works best for the kind of the job at hand, and then blending seamlessly between those different ways of working.
Exactly. And then also the really interesting part is we could easily hide those parameters. I mean, it's actually more work to show them to the users. But we really want to make a tool that is very, very powerful, and then strip away some features for the everyday user that they might not necessarily need it, but everything still under the hood is there. That if you want to build something exactly like you want it, then that's a great, then you can do that. And all of the tools are there.
Well, and I would imagine that if you're interested in having research scientists make use of the tool, then exposing some of that is, I mean, I guess in one way, they may never actually tweak it to switch from one to another, but just knowing that they can is probably reassuring to a lot of scientists, right?
Definitely.
It communicates something about the intention, yeah.
Yes, exactly. So there's usually always a drag between public presentations and scientists, where for scientists, on average, the more parameters you can tweak and manipulate, the better. But for regular presentations, you probably only want a handful of them, and then that make a good story. But then, depending on the story that you tell, it might be different sets of parameters.
Yeah. Well, I think since we're talking about scale, maybe it would be good to go ahead and, since we've got a whole universe to explore, maybe moving even out of the solar system for a bit.
Absolutely. So as I said, the stars that we have in the background, they're coming from the digital universe, and they're actually in their correct 3D position. So we on Earth have looked up at the night sky for millennia, and basically we connected stars that are roughly the same brightness together, and we call them constellations, which, if I go down the menu, we can look at what the constellations, actually, that's the wrong one. We're looking at these ones. So what the constellations look like. So here we have Orion, and well, these are of course just projections of 3D structures onto our hemisphere around us, essentially. So if we now zoom out, we can see something that is really fascinating, is mind-blowing every time you show it the first time to someone, is that naturally those stars are all at different distances. So when we're flying out, we can see how this projection actually unfolds. And this is one of those things that I find really useful when giving lectures on computer graphics, for example. Everything we're doing in computer graphics is projections. And this is one of the projections that humanity has done for thousands of years without actually realizing it.
It's ancient ray tracing.
Essentially, yes.
And what's amazing too, and is important to underscore, like, we vastly exceeded the speed of light in just the last few moments. I mean, we did it in going from Earth to Mars, but now we've really transformed in scale from something that was, like you were saying, basically human scale, looking at a resolution of like 25 centimeters out to now, light years in scale.
Yeah, so we're right now 107 parsecs away, so about 350 light years. So, like, if I put in as a size measure, so this is how far our collective radio signals have come so far. So yeah, we have been definitely exceeding the light speed by a dramatic factor.
So 60 years of sending radio transmissions out into space, traveling at the speed of light, and we get that far, and we traverse that in a couple seconds.
Exactly. But this also brings one of the interesting aspects of it, that we're actually, if we're looking at the surface of Earth, we can say that we're looking at something that was looking like that a couple of months ago, maybe, or so. If we're now out here, that is not that easy anymore, because we are looking now at the stars, how they're mapped from Earth, but our camera is no longer at Earth. So we would actually be seeing something different if we actually were to be here, but we don't have that information. And going back to the bathtub effect, we don't really want to show anything that is not real in a way.
Right, because in fact, all these stars are orbiting the center of the Milky Way, and their positions have actually physically changed in space in the amount of time since we've observed them, which is pretty wild.
Exactly.
Well, great. I think, I guess dealer's choice, what topic you'd like to address next, but I know that there's a new version of OpenSpace coming out, and I think we wanted to talk about that a bit. And I think kind of the same way we looked at the radio signature, the radiosphere, as we nicknamed it, around Earth. It's hard to think about radio signals and not think about searching for life elsewhere. And when you start thinking about searching for life, you start thinking about exoplanets. And I think there's some cool exoplanets that even my cat is getting excited about and making noise.
Yeah, so the exoplanets is one of those things that started out as a master thesis project from Karin Reidermann from 2 years ago, that has now been merged into the main branch, and this is one of the big things that we're going to add in this new release that will come out within the next 2 weeks or so. So we have from the Digital Universe database, we have markers of all of the exoplanets that have been discovered by various methods. But these ones, we can get the names, we can get the locations, and we can maybe get the numbers for some of them, but it's not really that complete. However, there are databases out there that collect all of this information to an immense amount of detail. So we've now added functionalities to tap into those databases. So that's done over here with this new UI, where we have a list of all of the known exoplanet systems. So, for instance, what we can do if we just pick probably the most famous one, the TRAPPIST system. So it works for a second as it goes out, gets all of the information, and now we have the star here. So now I can refocus the camera, and instead of zooming back into Mars or Earth, now we're flying over to the TRAPPIST system, and we're visualizing everything that we know about that at the moment. And this is a very small system, so it takes a while to fly in. So here we have the star in the center, and all of its, I think, 7 planets. And you can also see like a little rainbow around them. So here is where we show one of the uncertainty of the orbit for each of the planets. So if I rotate this down a bit, you can see like same thing as we saw with Earth. You have the trail of the planet over here, and then surrounding this trail is the area of 1 sigma. So like 68% probability that the orbit is actually in between these two values.
So we did a question about the where in basically Earth's sky the most exoplanets have been discovered. Are they kind of all in one part of the sky or all around?
Well, let's actually look, right? The beauty of having a
visualization tool.
Yeah. So if we're flying back to Earth now, solar system, close enough. And now if we're looking at all of the exoplanet systems, so we can actually start looking around. And if my orientation is not completely off, we should be seeing one area soon that is, there we go.
Like the others, yeah.
Exactly. So here we have one of the areas on the sky where we have surprisingly a lot of discoveries. This is one of those things that if you don't know anything about the subject, you might turn on the exoplanets, look around, and you see like this area, and it's like, okay, why is there so many more exoplanets in there? But then, like looking around it a bit, you can see that, for instance, there's like this. It looks almost like a square, but then there are these areas missing. And now I don't have it prepared because I didn't know this question was coming. But this is following exactly the layout of the Kepler instrument. So the Kepler instrument is basically a square with these corners cut out. So this is all of the exoplanets that have been discovered by the Kepler instrument. So this is one of those things where looking at it from the Earth, you see it, but then if we're flying out, we can actually see that same thing as with the constellations. All of these exoplanets are tracing out a cone in the night sky.
And it's basically like the kind of like looking for your keys under the lamplight. It's like if you've searched that part of the sky really, really carefully, you end up with lots of discoveries there. So yeah, our missions haven't exactly uniformly scanned the sky for exoplanets. But
exactly. Even more impressive version of this is if we fly out even further. So we're looking at the Milky Way galaxy. We're looking at our closest galaxies from the Tully data set. But if we're exceeding even that, so you can see we're way out here right now.
Right.
So here we're seeing what most people call like the butterfly, which is the Sloan data set, the SDSS, the Sloan Digital Sky Survey. So this one is a data set of galaxies that reaches out to almost like the edge of the known universe, the observable universe. But it's missing areas in the sky where there are no real galaxies that are shown. So this is one of the another area where we can see the same thing. It's like we only have looked into these particular 2 directions. And you might be wondering, it's like, why only these 2 directions? So if I were to overlay the galaxy, our Milky Way, on top of this now, the Milky Way would be exactly aligned with the center of this butterfly. And because the Milky Way is full of stuff, we can't really point our telescopes through the Milky Way. So it's much harder to discover galaxies in these areas of obscuration. So like we're looking up and down out of the Milky Way. So this is another one of those areas where it's unlikely that the universe actually looks like this, but
Right.
we're only showing the data that's actually there, or that we actually have.
Which is, of course, an interesting message when you think about all these things, which is like just showing the data as we understand it, as we see it, is in itself, a really important story.
Yes. And the measure of how we discover it as well.
Well,
like looking at the Kepler.
I feel bad because we interrupted your description of the uncertainty around in the orbits around TRAPPIST-1. I don't know if you want to go back to TRAPPIST-1 or to some other exoplanet system, but I think that's a really cool concept. So I think it would be great to kind of return to that if we had a moment.
Sure.
We're doing okay on time.
I'll just focus and zoom in very quickly now. So now we're flying into the TRAPPIST system. We're closing in on one of those markers, which is like great. Because that kind of, and here, so this one I haven't seen myself before, but you can see like the marker for the TRAPPIST system is like flickering about. I'm not sure if that comes over on the stream because it's flickering quite quickly. Mm-hmm. Same thing with the floating point problem that we were looking at before. It's like we're rendering this one at a too low resolution, so it starts flickering. So we just get rid of that very quickly.
But again, we did just traverse, hundreds of
almost
light years. So.
Exactly. Almost the entire known universe. So we have, right now we're only showing the uncertainty of one of the orbital parameters. And this is one of the open research questions that we're looking into right now of how do we actually visualize the uncertainty of an entire the orbits are basically a 6-dimensional object. Right. And like, how do you visualize that so that it's actually meaningful to both the public, but also to exoplanet specialists that want to look at the data to see maybe are there trends in the uncertainty and so forth. So there's a tremendous amount of scientific visualization research that comes out of this as well.
Yeah, because that's a hot topic in visualization in general, how to depict uncertainty, because it's such an important concept, and yet one that often is sort of ignored in public discourse and the way we talk about everything from the trajectory of a hurricane to errors in poll results, for example, related to elections. I don't know, just to choose a random example. And visualizing uncertainty is a huge, huge question. So here you're seeing basically the blue represents kind of the outer limit, and the red is sort of the inner limit within a specific statistical bound.
Exactly.
Yeah.
And the blue and the red is because, well, the closer you are to the star, the hotter the surface is. So there's this visualization principle baked in as well, that we associate colors with specific things.
Right.
But yeah, this is only one of the potential uncertainty, the ways how we can represent uncertainty. And yeah, as you said, it's a very hot topic, and particularly domain scientists, they're very, very interested in knowing what the uncertainty for specific values are, because like if you just give them a value, it doesn't really mean anything unless you can also say how certain you are about it.
Absolutely. Cool. It's a very, very spiffy.
Yeah, but basically with this, you can go into whatever exoplanet system you want, and it will grab the data. And the nice thing is that the next time I start OpenSpace and maybe someone has discovered another planet in TRAPPIST, which is very unlikely, but if it happened, next time it would just show up automatically. So there's no manual creation there either, which might hold some of the data back, which I think is very, very, very good.
Very cool. Well, I think we are kind of coming close up on time. I don't know if there was anything else that you really wanted to dig into, but I certainly think we want to talk about the open source quality of OpenSpace.
Absolutely. So yeah, I mean, it's a very, very large international collaboration that's going on. So we have from the university side, my own university, Linköping University, my other own university, the University of Utah in Salt Lake City, and then New York University in New York, as the university partners on the project. So that's like the academic-driven side of the development. And then we have currently 6 ISR partners, of the Morrison Planetarium, one of them, as our outreach partners that we can work with and get very, very useful feedback from in the field, to not have this ivory tower kind of feeling. But yeah, so we have 7 developers that are working on the software right now. So 3 of them, me including, sitting here in Sweden, and 4 being located in the US. And we're very, very, very lucky in 2015, or very grateful in 2015, to get a grant from NASA to continue the development of this for public outreach, which has kickstarted this project quite a lot. So we had our first big show in July of 2015 with the New Horizons flyby at Pluto. And I think that got people excited in the capability of showing what missions actually do. So we can, we started doing that, and we got just renewed this year as well, which is very, very, very nice.
Very encouraging. Yeah, and really, we didn't even touch on some of the cool spacecrafts visualizations, which are a core part of OpenSpace as well. Well, I guess it's worth noting too that really anyone can be engaged in this process, because OpenSpace, being open source, is, there's a GitHub link that we could share, but if you are interested in downloading it, you can do that from the OpenSpace project website, which I think we've already shared, but you welcome feedback from users.
Absolutely. I mean, the more feedback we can get, the better the software becomes. So yeah, as you mentioned, there's the OpenSpace project webpage, which has the pre-built binaries, the turnkey solution of like just downloading it, starting it up, and you basically can do what we just did here. But then there's also the GitHub repository under the same name, which allows access directly to the source code. To maybe, if some people that are watching are interested in contributing, we're very, very eager to get people working on that. But also just providing bug fixes, like, oh, I did this and this, and the program crashed without a message. It's like, yeah, those things are the things that we really want to learn about in order to make it better. And this is ultimately what this whole project is about, to educate the population on a number of different levels, and like the more the merrier.
And there are also ways that people can contribute data sets if they wanted to build out a data set.
Yeah, definitely. So we, in our documentation, we distinguish between 3 potential use cases, or different groups of users. So on the one side, we have what we call users. Those are the people that download the software, give a presentation as I did just now, and just explain a topic to a general audience, or maybe they're discovering things by themselves. So those would be using the software, using the menu system and everything. Then the second group of people that we call builders. So those are people that make use of the existing infrastructure to make something new. So this could be, for example, we were looking at the CTX layers. Maybe there's another one that we would want to put in. So there's a very easy interface for just putting in new layers. And then lastly, we have developers, which actually go into the C++ code to actually write something completely new and novel. So there's like all of these 3 different options to contribute, which we all value equally.
Very cool. Well, I don't see any other questions. I don't know if you had any other closing thoughts.
No, it's just I'm very grateful to, as I said, very happy to be here, and very happy to basically run this collaboration, which is now 5 years old now, and been
and counting. Yes.
Yes, exactly.
And although you've been watching at home, you've been seeing the streaming on via the Facebook or YouTube channel. This is the same software we run in Morrison Planetarium. We are, fingers crossed, going to be opening Morrison Planetarium soon, pending some details to be sorted out, and of course, pending good numbers for the current pandemic. But someday soon, perhaps you'll be able to see it in Morrison Planetarium. Until then, we are doing a lot of streaming like this program. But every Wednesday at 4:30 Pacific time, you can catch a tour of the universe that uses OpenSpace and get a little bit more of a look at some of the things that you can do with it. And I'll just note that next Friday at this time, 11:30 a.m. Pacific time, we'll be talking to Jackie Faraday from the American Museum of Natural History, and a great exploration of an amazing data set called the Gaia data set of literally, just a ridiculous number of stars.
Yeah.
You thought you saw a lot of stars in this program. Nothing compared to
that's it's over a billion stars. Which...
Yes, and so and she'll be talking a little bit too about some of the research potential for this kind of visualization software. So hope you can join us then. Well, thank you very much, Alex, for taking the time out of your evening in Sweden to talk to us. And thanks to everyone who joined us on the OpenSpace YouTube page and the Morrison Planetarium Facebook page. We'll look forward to seeing you again virtually or perhaps someday soon in Morrison Planetarium. So take care.